Welcome to This Explainer. Today, we're diving into the totally astonishing era of human computation. We're talking paper, pencil, and just sheer genius laying the absolute foundation for modern spaceflight. We live in this world that's entirely driven by digital automation, but really, not that long ago, the most complex systems in the universe were decoded by human minds, step by meticulous step. To really get the stakes of early aerospace engineering, we got to ask ourselves a pretty fundamental question. How exactly did humanity solve the world's most insanely complex mathematical problems before electronic processors even existed? Seriously, imagine trying to map the exact path of a spacecraft moving at thousands of miles an hour. You've got to factor in the rotation of the Earth, the pull of gravity, all using nothing but your brain and some mechanical tools. Wild, right?
It's honestly mind-boggling when you think about it. We hold literal supercomputers in our pockets today. But back in the 1940s, critical differential equations and these incredibly precise billionth of a second blast wave simulations were solved by human calculators. During the Manhattan Project, this was mostly women just churning out massive, complex numbers on these clunky, super slow mechanical desk machines. We're talking Marchant, Friedan, and Monroe calculators. They were basically doing human parallel processing, passing equations down a line to do by hand what a microchip does today in a fraction of a millisecond.
Now, the environment they worked in? Definitely not equitable. One Los Alamos department head is actually rumored to have said they hired girls because, and I quote, they work better and they're cheaper. Yeah. But here's the thing. Despite facing that kind of blatant workplace inequality and often doing the absolute most tedious calculations for hours on end, these pioneering women gained the technical experience that quite literally triggered the development of the world's first electronic computers. So their manual labor absolutely paved the way for the digital age we're in now.
So let's get into Section 1, Zooming In, the Math of Spaceflight.
Zooming in from the atomic era to the dawn of the space race, the math shifted from calculating blast waves to something even more staggering: orbital mechanics. Take a look at this. It's a September 1960 NASA technical note, designated D233, co-authored by T.H. Skupinski and the absolute legend herself, Katherine G. Johnson. This isn't just a memo, guys. It is an incredibly dense mathematical roadmap. Its entire purpose was to figure out how to place a satellite over a precise, pre-selected position on Earth after a specific number of orbits. Okay, to demystify this report a bit, we need to understand exactly what Johnson was trying to solve. The math here revolves around two huge concepts: the burnout position and the azimuth angle. So burnout is just that exact moment and location where a rocket engine shuts off, right? And the spacecraft begins to coast in freefall. The azimuth angle is the precise directional angle, measured clockwise from north, that the spacecraft has to be traveling at that exact instant. The whole crucial point here was that Johnson had to determine the perfect azimuth angle at burnout to guarantee the spacecraft would eventually pass right over a safe recovery area, like a specific drop zone in the ocean. And the actual math behind this is just stunning. Digging into page 6 of her equations right here, you can see Johnson didn't just, draw a line on a map. She used complex spherical triangle relations to connect a satellite's orbital plane to its projected trace on the Earth's surface. She was calculating time from perigee, which is the closest point in the orbit, and something called eccentric anomaly. Think of it like this. She was essentially projecting a massive invisible triangle from the center of the Earth all the way out into space and using trigonometry to predict the future. But wait, it gets harder. The Earth rotates beneath the satellite, right? And the Earth isn't even a perfect sphere anyway. It's oblate, meaning it bulges at the equator. So Johnson actually had to develop this rigorous step-by-step iterative procedure. First, estimate the time from perigee, calculate an initial azimuth, then factor in that oblateness, and then recalculate the whole thing over and over again. She did this iteratively until the numbers converged and perfectly aligned. Just an astonishing feat of mental endurance and precision.
And Johnson wasn't just working in theory here. She meticulously proved her method by running actual test cases. For instance, calculating eastward launch, case A, down to 1,000th of a degree. She then validated her handwritten, iterative math against early electronic data run on an IBM 704 computing machine and showed incredibly good agreement. Basically, her human mind was going toe-to-toe with an early supercomputer and winning.
Her grasp of this three-dimensional geometry was so masterful and honestly so trusted that it led to one of the most famous moments in space history. Right before astronaut John Glenn took his historic orbital flight, he didn't fully trust those new electronic IBM computers. I mean, would you? He famously refused to fly until Johnson herself, literally sitting at her desk practicing with a globe known as a celestial training device, checked the mechanical computer's math and verified the trajectory by hand. Moving right along to Section 2, the machine transition and hidden legacies. So as we step out of the math equations and into the digital modern aerospace age, the world was changing rapidly. As electronic computers arrived at NASA, they really threatened to make human calculation completely obsolete. But Johnson's colleagues adapted brilliantly. Dorothy Vaughan foresaw the shift, independently taught herself the Fortran programming language, and then actually trained her colleagues. She went on to contribute heavily to NASA's Scout Market program. Meanwhile, you have Mary Jackson breaking immense barriers to become NASA's first Black female aeronautical engineer. Later in her career, she actually took a demotion to move into management so she could dedicate herself to championing the hiring and promotion of the next generation of female scientists. Talk about legacy. Now, alongside the brilliant women of NACA and NASA, the World War II era also gave us other hidden intellects. Take inventress and actress Hedy Lamarr. Lamarr brilliantly co-developed a frequency-hopping or spread spectrum system. The whole goal was to prevent radio signals for torpedoes from being jammed. How? By randomly hopping from frequency to frequency simultaneously between a transmitter and a receiver. So what you should really take away from all this is how these specific theoretical milestones directly built your modern reality. The tedious work of those Manhattan Project calculators, that triggered the development of the electronic computer. Katherine Johnson's incredibly complex orbital math, that laid the groundwork not just for Mercury but for the Apollo moon landings, the Space Shuttle, and even modern parameters for Mars missions. And Hedy Lamarr's frequency hopping is the exact foundation for the secure Wi-Fi and GPS systems that you are probably using right now. These achievements are honestly even more incredible when you stop and consider the context. Working in an era of segregated bathrooms and immense prejudice, Katherine Johnson noted that the absolute truth of her mathematics ultimately cut through the discrimination of the time. Because math has no bias. As she said, and this is a quote, "They never asked me to go back over my calculations because when I did it, I had done my best and it was right." And Mary Jackson's profound words perfectly capture the immense courage required by these women. Doubt kills more dreams than failure ever will. They had to push beyond severe societal limits, systemic racism and sexism, to quite literally engineer the future. They just didn't let doubt stop them from mastering the unknown. Which leaves us with a final, fascinating question to ponder long after this explainer ends. We are currently sitting on the absolute edge of new frontiers: commercial space travel, artificial intelligence. So, who are the hidden figures today? Who is sitting quietly at their desk, calculating the breakthroughs of tomorrow? Keep an eye out for them, because their math just might change your world. Thanks for learning with us.